In the video number 17 in the Foundations of the Computational Economics course, we are using Pandas and Numpy in a small exercise to implement a linear regression model. So here's a short, let me actually go to the normal notebook view. Here's a short description of how you do linear regression models using matrix notation, and that's what we are going to be doing. We assume a linear relationship between the dependent variable y and several independent variables which are collected in the matrix X, column by column. The task is to estimate the vector of coefficients beta, and by minimizing the sum of squares of the residuals given with this formula, right, just the difference between the prediction and the observed y. By minimizing the sum of squared residuals, we obtain a very well-known formula of x prime x inverse x prime y. Now, we're not only interested in the estimates, but also we would like to get a grip on the reliability of this estimates, and therefore we want to estimate the variance matrix for beta, and this is given by this formula here. S square is the estimate for the sigma square in the distribution of the error terms, and it's called the mean standard error. It's also, it's estimated in the simplest way, also using a quite simple formula. Okay, so the goal is to write the function OLS, which takes the independent variables as a matrix X, dependent variable as Y. Now, it may add a constant to X to allow for the constant term in the estimates. And we want to print a report if verbosity is not set to false. Okay, so let's just start with implementing all of the formulas. Assuming that X is already given as a matrix with data arranged in columns, we can say X transpose matrix multiplication X, and this needs to be taken in inverse. I'm implementing the formula for beta. Now, what's the inverse of the matrix? Let's just ask Google. There we are. Numpy inverse matrix. This is just numpy .leanalg.inf. Numpy is already imported, so I can use np leanalg.inf. That's the inverse, and then we have to multiply with matrix multiplication again by X transpose Y. So this is the expression for beta. And again, I'm assuming that y is a column vector here. All right, let's find the residuals. Remember, residuals is just y minus the x times beta. Okay, the s square, the mean standard error, will be approximated. Estimated using the sum of squares of the residuals, and that can be calculated by transposed E times E, and this is essentially dot product of the residuals, and we have to divide by the difference between the number of observations and number of parameters. Now, how do we find that? Well, that's essentially a shape of our data. Right, because the number of rows in the X is the number of observations, and we estimate the same number of parameters if there are columns in X. Okay, and then finally, the variance-covariance matrix of X is given by the X transpose X inverse times the S square. Okay, that's all. That's all of the formulas from the previous slide, from this slide. implemented, and we can return, what do we return? Beta and sigma. Okay, let's run some tests, and we have some tests here in the next cell. And if I run this, there is nothing printed, of course, but let's first look what's going on in this cell. So X is given here as a two-dimensional NumPy array with data organized in columns. Now true beta is the vector of true parameters that we want to check whether we can estimate using OLS. And then Y, the dependent variable, is actually given by the formula of X times true beta plus 2.5 for a constant, and then some random component, their errors. To see all of this, let's print X, true beta, Y, and I want to separate my printouts with double new lines. Sep, that's what was meant here. Okay, so here's our X vector. Vector, the matrix, X matrix, the data matrix. You can see that true parameter, the true beta, is the column vector in here. And so how do we do that? If we only had this expression, right? So we take two numbers from the list, from normal Python list, and convert them to the NumPy array, then we would have something that looks like that, right? And notice just the single bracket. If I print here the shape of the true beta, let me comment this out and print type and then shape. We can see that this are two numbers. They're NumPy in the array, but they are one-dimensional array. The shape gives the number of elements in each dimension, and so this is a one-dimensional array. We can also use the function true beta and dim to see that there's only one dimension in this array. Now, by adding this strange-looking slicing expression, I'm telling NumPy that I want these two numbers to be arranged along the first axis, and the second axis should be new axis, so it will only have one element. So let's see what happens now. Now with this, which is a standard way for NumPy to convert from one-dimensional to two-dimensional arrays, or three-dimensional if we can add more new axes here. We get a column vector which has two dimensions and which shape is 2 by 1. Now, what do you think happens if we have this expression? Now we are saying that the first axis should be new, and then the data should be arranged along the second axis, and then we get a column, the row vector. Well, I want a column vector in this case, because then it is multiplied with X using standard matrix multiplication, and so we do need a column vector in there, and that's what we have. And here is the data for the dependent variable Y. Now we are adding some normally distributed errors of the correct size, right? And with the scale equals 0.2, which is a sigma parameter in the normal distribution, essentially. Okay, so this is our test case. And now we will run our function. The function doesn't produce any output, so let's just print beta s, and again I want the double line separation. So here's the estimated beta, a column vector, and a matrix S. All right, let's come back to our function, and let's start working on that further. First, let's do a report. If verbose, then let's print number of observations. And I want to use the dot format notation. Number of observations is n. Number of parameters. Number of parameters is k, as we said already. Now I want to do a mean standard error equals, and let's give it some precision, 0.5 f. That basically says that I want to print 5 digits after the decimal dot. And here s square, well, s square is a mean standard error. I want mean standard deviation. So maybe we can calculate it here as well by taking the root of s square. Okay, let's stop here and test this. Oh, and we get a problem. What's the problem? So it prints number of observations and number of parameters. And then unsupported format string passed to num array. So that's the problem. Okay, well, let's see. If we just put a number here, will there be a problem? In the inspect module. That's interesting. I guess I just forgot to run this function, and if we do it again, we don't have an error actually. And what do we have? Number and MSE is printed to equal a particular value. Okay, so but I want to print s. Why can't it not print s? It seems to give an error when I'm trying to print s over here. Well, let's try to investigate. Let's do the same thing. Print s, type of s, s and dim, and s shape. Just to get an idea of what s actually is. So s is in the array. It has 2 dimensions, and its shape is 1 by 1. Okay, so it seems that the print format is having troubles printing s as a 1 by 1 NumPy array. Okay, well, but this is just a scalar, right? So why can't we just have it as a scalar? In fact, this np.sqrt, the square root of s2, that's a NumPy array. And if I take just the first element, right, by saying 0, 0, I'm explicitly taking the first element. Now this should be corrected. Yeah. Oh, let's look again. Okay, so now it's just a float. It's a constant, and of course it has no dimensions, and the shape is nothing, because that's just a it's not even an array anymore. Yes. Okay, we've solved this, and now I want to print the estimated coefficients, the estimates, and their standard errors. So I want to print b as element of beta, and s as the elements of, well, s is already taken, std. This will come from beta and the diagonal of sigma. We can calculate the standard errors for beta over here. We need the diagonal of sigma matrix, but also we need to take the square root of these elements for the standard deviations, right? The diagonal of the variance covariance matrix has the variances of the parameters, but we want standard deviations. Okay, so beta and beta as standard deviations. Now remember this function zip, which combines element by element the elements of 2 arrays into into a pair, into tuples of two elements, and this is what we are assigning them to. And so I just need to say print, and let me have a long field here for beta, format beta std, and I'll print the standard deviation in parentheses. Okay, that's what I'm. Of course, this needs to be in. That was a bug. Okay, we get an error as well. And again, it's the unsupported format string passed to NumPy array. So let me just print, the same diagnostics for beta and standard deviation of beta. So B, type of B, B and dim, and B shape. B is the NumPy array of one element with one dimension. With one dimension, one element in the first axis. Okay, and what about the standard deviation? Can probably have written the function already to run this, to print this diagnostics. And the standard deviation is just a float. Okay, so it must be that the B is the problem. All right, it's over here. So if B is the problem, then I just want to say that B should be the first element of that vector. How about now? Okay, now everything prints. Now everything prints as it should. Here's the final output. Is it? Yes, we just need to delete that. Okay, number of observations is 10. Number of parameters to be estimated is 2. The mean squared error is 0.91. And then these are the estimates. Now, we do know the true value of the parameters, right? They're here, 1.234. And instead we get 1.67 and minus 0.345. We get something completely different, and the mean square error should be the estimate for the scale parameter of the error term, and it's kind of off as well. And where's this 2.5, which is the constant in our linear regression? Well, that's actually the problem, right? We need to include the constant, and for that we have a special parameter here. And so we need to add a column of ones into the matrix X if this parameter is true. So if add constant, add column of ones to X. So how do we do that? Let's see. NumPy concatenate horizontally. And I want the docs. NumPy arc, NumPy concatenate. I'm looking for a function which is hstack arrays in sequence horizontally, column-wise. So NumPy hstack top is what? Sequence of NT arrays. So that's what we need. So we need to say that X is going to be MP hstack of ones and then the X, right? And this needs to be a tuple in itself. So we need to give a tuple as an argument. So what's the column of ones? That's ones. And we need to give it a size. Let's check what arguments does ones take. NumPy ones. Manual shape. Okay, we just need to give it a shape. as shape as int or sequence of ints. So another tuple. So here I want to give it a sequence. It's going to have one width of one column, and what's the number of elements vertically? Well, that's the number of elements in shape of x at sorry, 0th index, right? That's the number of columns in x is simply x shape 0. Okay. So this now should add a column of 1s to x. And let's run it, and indeed, we get this additional estimate, and this seems to be close to the constant 2.5 that we gave. So let's check the other estimates. MSE is estimated at 0.12. It's a little bit lower than 0.2, but how about these? 1, 2, 3, 4. It's 1, 1, 2. It's a little bit lower, but this is pretty close. And now the standard deviations of the parameters show that they're definitely less in absolute terms than half of the estimated. We didn't explicitly code the t-test in here, but you can see that all the parameters are estimated sharply. All right, so it seems that this test has gone well. What about this add constant false? I guess that will also work. And we'll get the what we had before. This is another call of the OLS function. Okay, so it works. And let's move on to this other example. Now, here's the difference. So let's try to run this one. Oh, it gives errors again. So what's going on here? Well, see, what if x is not given in the matrix as we are expecting? So here x is just a NumPy array of some numbers, so this has a dimension of 1. And where the error that pops up, here's the value error. All the input arrays must have the same number of dimensions. Okay, that's on some function that is internally called. So there's a whole bunch of errors here. But let's think what's going on. I should find something that that our call is causing. Render transmitter. I don't quite understand this message. But here's what I think is going on. We have add constant equals true. Isn't it right in here? Yes. So when the code gets to this line, we are asking for the shape of x with 0. No, that's actually right. So maybe it's this one that's not working. Okay, let's see. I had to restart the kernel to get back to the normal error messages that are the ones that we usually see. I don't know what was going on with my Jupyter notebook. Apparently there was a problem there. But so none of the code has changed. And so let's see what error message are we getting. All of the input might be the same size. Where's this concatenate? So it's concatenate that's giving us the trouble. All right, so let's see, let's think about what's going on here. So x shape of 0, that's going to be just one number, and whatever the shape of this vector happens to be, it's 10. There's one dimension in x, and x shape 0 will give us the number of elements along that one dimension. But here we are creating the NP1s. We are creating this as a column vector of 1s. And so concatenating the h-stacking the column vector of 1s and a unidimensional, one-dimensional array x, that's what's not working. So what can we do here? Well, we should probably check on the number of dimensions of x just in the beginning. And we know there's a property ndim. So if ndim equals what should we check? Doesn't equal 2, I suppose. We need to do something. Or let's rather check if ndim equals 1. Then we can say just that x is going to be an x where we put all of the data into the first array, and then new axis is going to be the second axis. So we are converting the one-dimensional x array into a column vector. Okay, let's try this. We get another problem here. Invariant index to scalar variable. That probably has to do with the fact that our y is now also unidimensional. And that means that this, I'm not sure what this is, x dot beta. That probably that e becomes unidimensional. And then s square becomes that becomes a scalar. And s is now just a scalar, but we are trying to index into the scalar. Okay, so I guess the simplest thing is to check whether y ndim equals 1, and then say y equals y and do the same trick. Let's see if this will pass now. And it does. And what about the second call? And I think it does as well. Okay, so now we've modified the OLS procedure such that it works both with the vectors of dependent and independent variable of one dimension or multiple dimensions. Well, let's see if it holds further. Before I attacked the same problem in a slightly different manner, and here is an OLS, let's call it OLS 2. Here, I'm taking a different approach. I'm squeezing the y in case it was a two-dimensional array to be a one-dimensional array. And then you can see this more complicated if statement where I'm also conditioning on whether x has one dimension or not. And x here becomes a two-dimensional array in a similar manner that we did. Okay, but y is one-dimensional. And that changes the program slightly. Oh, this inverse is pre-computed here, which is a good idea for for efficiency. And so if y is unidimensional, then the s square is just a scalar, right? And here in the output, I guess yes, it's just the square root of s2, which is just in the output. And so we don't need this additional step of taking the first element. And as you can see, there are two approaches to dealing with the same issue, but it's very important to note that the NumPy arrays, the ND arrays, they have a number of dimensions, and a lot of the times the NumPy does not keep information about the second unitary dimension if it doesn't have to. And there are essentially two ways to work with these arrays when you're doing linear algebra. Whether you want to keep it in full dimensions, 2 dimensions all the time for vectors and matrices, or you want to work with unit-dimensional, one-dimensional objects as well. You just have to be aware of this and correct the code, write the code accordingly. All right, so let's move on and look at the data now. We're going to be looking at the data which is the same as in video 15 on Pandas. This is the data set on the median earnings and different college majors. We load the data set as well as in the same way. So we import Pandas as PD, and then we just read comma-separated value file. Let's look at the variables that are in the file. This is the info statement, as you remember. Here's the 21 different columns, the data types, what we have 172 observations in this data set. Looking at the first 15 rows of the data, we see all of the columns. Some of the columns are text, but most of them are not. They are numbers. And remember this plot from video 15, which plots the share of women in different college majors and the median salary. The question that I posed in the lecture was that whether there's a downward sloping relationship here. Well, we can check it by running a linear regression between these two variables and drawing the line that would approximate the relationship represented by these dots. Let's do that now that we have the OLS function. Let's just do it here. How do we do it? We have to call OLS and give it the dependent variable and independent variable, right? Well, not to confuse things, let me use the labels for these arguments. So what should be x? X should be data, and then the independent variable, that's share of women. And here, data median. We want constant, and let's look at the output as well. And I'm commenting out just for now. I'm commenting out the comments which make the plot. Let's just look at the OLS. Oh, so OLS works, right? But it estimates the nans from 173 observations, 2 parameters, and we should expect 2 parameters. It should add a constant. Why do we get nans? It's a little bit unexpected. And you could think that the code is wrong here, but we've tested the code using this data. So maybe it's the data which is the problem. How do we... is it possible to check if we have nans in the data? Or have some problems in the data? How do we do that? Well, we could go back to head and try to, plot... just print out a whole bunch of data and look through it. And even more so, let's look only at the columns that we're interested in, which is share, women, and median. And remember, when we are asking for multiple columns, then we have to give it a double list. There we are. Oh, I see a nan. Over here, there's a nan in the share women. And of course, that's going to spoil all of the computations that there are. The other way to check for nans in the code is to run this line here, which I take from the solution that I've coded up before. And you can see that the median has no nans. So what are we doing here? We're just printing, we're taking the data, applying a function is null, and then taking the sum. So is null is going to give us true or false, which is 0 and 1, and the sum will count the number of appearances of nuns. And you can see that in share of women, we have a none. Okay, how do we get rid of nuns? Pandas, drop nans. And it turns out that there is a command, drop NA, which we can use on our data set and clean it up. Okay, let's probably do it right in the beginning before we start analyzing this data. It's called data1 is data. Take only the variables that we need. And apply drop NA. And now I have to correct all of the calls to the data, data1, data1, and data1. So what do we have now? Here's the number of observations. Here's our estimates. Okay, we don't actually need to see them. So let me say verbose equals false. But what we do need, we want to plot another line. And, well, let this line sit on the supportive axis. So I'll create a grid over x using linspace. The boundaries here are between 0 and 1. And let's put 100 points. And for the line, let me create a lambda function of x that will simply take beta 0 plus beta 1 times x, where beta is of course coming from the OLS regression. Okay, and I just need to plot it. So x and y in this plot. Oh, there seems to be a problem. Couldn't be broadcast together with shapes 2, 2, and 100. Okay, broadcasting doesn't work because the objects are of different shapes. And what are these different objects? This is in lambda function. So we are multiplying this. Now, I thought that beta 1 would be just a scalar, but okay, so remember that OLS outputs 2 arguments, so we need a sigma argument. We actually in Python you can just say underscore, and that basically uses the underscore as a variable, and this is a legal variable name actually, to forget the output that we don't need. So we will only need the beta. And here we are. So is this a significant decline? So let's look at the outputs of the regression as well. This parameter is huge, and that's because the dependent variables in dollars. So it's minus 30,000 plus minus the the standard deviation is about 3,000. So it's definitely a significant coefficient that we've estimated. Okay, here's the code that should achieve the same. Except it doesn't. Okay, what's going on here? Where's the line? It still works with nans. Drop nans from data. Yeah, it needs to work on data 1 in order to create a line. And you can see here I'm also adding some parameters to the line, which is color and the line width. Okay, so if we want to run a multivariate regression, we can still do it with the same function, of course. And let's see what's going on here. We can create some fraction variables as employment rate and full-time rate. I thought, these would be interesting to explain the differences in the salary, in the median salary. And in order to ensure that these ratios are correct, I'm running these two functions. I'm dropping the observations from the data which have total equals 0 or employed equals 0, just to avoid division by zeros. Okay, and then we can also drop nans to create this data set 2. And I'm also scaling the salary by 1,000, so we're expressing the median salary in $1,000 rather than dollars. Okay, and this is the data cleaning part that we've done, and now we can run a full model, run the model with multivariate regression, and you can see that the share of women, this is a constant, the share of women has now a minus 27, so minus $27,000 a coefficient, which is smaller, right? Why is that? Well, that's because the other parameters, employment rate and full-time rate, also take on some of the explaining of the differences in the median salary. although the employment rate seems to be insignificant, right? So the standard deviation is really close to the estimate in the absolute terms. And so this is insignificantly different from 0. But the full-time rate for the jobs that have more of the full-time, for the majors which correspond more to the full-time job, that's where the salary seems to be higher significantly. Okay, that's all for this practical exercise. For further learning resources, you can look at a regression done at the CompEcon data science section using sklearn, a library which actually implements the modeling tools that we had to work with by hand here. But that was an exercise in linear algebra. All right, see you next time.